Text-to-image models scale with model size, data, and compute. We study a fourth axis nobody measures: the information the caption carries. It obeys a scaling law, and scaling it deliberately leads open-weight models on nearly every compositional and world knowledge benchmark. Here's the argument, starting with why the obvious approach fails. Give a generator one short prompt, and it returns an image dense with objects, attributes, layout, and text. The model supplied all of that, not you. So to control it, that detail must be written at the captioning stage. The obvious move, a longer caption, fails. On Detail Master, accuracy declines across 12 models as captions grow. 2 of these 3 captions are 30 words, but one adds 12 facts and the other adds none. Length and information came apart. So we measure information. 2 independent ways, and here's the first. Grounded perplexity gain scores every caption token under a frozen vision language model, once without the image and once with it. Whatever the likelihood rises by is information the image supplied. Summed over tokens, that's GPG. But it needs token log probabilities, so it only works on open models. So the second measure never touches them. Effective detailness has one model propose attribute questions from the image alone, and another check which the caption answers, and whether anything it claims is unsupported. Precision and recall, combined, so invented detail is punished harder than omission. 2 rulers, completely different machinery. This is the controlled sweep. Fix the backbone and the budget, vary only the caption. 15 configurations, each training its own diffuser to the same matched token budget. Top row, structured props separate cleanly by detail level, natural language captions collapse together, and length does not predict loss. Bottom row is the law. Converged loss falls linearly in GPG, and as a power law in ED, and the 2 measures agree on the ranking at a Spearman row of 0.96. Information is the bottleneck, not length. It splits in 2. Quality factorizes into diffusability, how well a caption format exposes image information for the diffuser, times promptability, how well a language model instantiates that format from what a user typed. The split matters because at training time, you have the paired image to annotate from. At inference, you have only the request. Diffusability first. Free-form language saturates. Extra tokens are paraphrase, not new conditioning. So we serialize images into named slots at 3 scopes: global scene and photography, per-element captions with boxes and depth, and cross-element relations. Detail now grows by filling slots, so every added token is a real field value. That raises the ceiling. That's promptability. Holding the schema and diffuser completely fixed, we sweep 6 Quen 3.5 checkpoints from 0.8 billion to 397 billion. Geneval++ goes from 46.4% to 86.8, over 40 points, diffuser untouched. So general language model progress transfers straight through. But zero-shot filling still leaves detail on the table. So we train the prompter. Supervised fine-tuning learns plausible schema content, not just valid JSON. A cold start teaches it to derive that content without ever seeing an image. Then reinforcement on its own rollouts, gated by a verifier and supervised token by token from an image-conditioned teacher. Watch the columns. Same prompt, same backbone, only the training stage changes. Put that trained prompter in front of the SP-trained diffuser, and we lead every column. The 2 rows worth pausing on are the controls. Quen image with its own official prompt enhancer, and a matched natural language run that changes only the caption representation. One thing we haven't used yet. Because the schema exposes decisions as named fields, a critique becomes a targeted field edit rather than a rewrite. So we close a refine render judge loop. At 8 rounds, the trained prompter reaches 54.3% preference, above the 44.7% of the strongest coding agent. But 8 rounds of the base prompter still lose to 1 shot of the trained one. Here's what all of that buys, head-to-head, hours on the right. A basketball and a violin, either side of a net, with the basketball closer. A spatial relation, not just 2 objects. And a kitten whose reflection is a panther, where the reflection must deliberately disagree with what it reflects. And the hardest case of all, dense, legible, structured text, where layout and spelling must both be right. This is where explicit layout fields pay off most. Position and text are conditioning variables, not things the model has to guess. So, to close, text-to-image quality depends not only on the model that renders the image, but on the information carried by what you condition it on. That axis is measurable. It obeys a scaling law, and it is worth scaling deliberately. Thanks for watching.